The process of electrically connecting any metallic object to the earth is called earthing or grounding. Earthing systems are designed to manage the flow of fault currents to protect people and equipment. Fault currents, including the lightning currents, are safely transferred into the earth through the earth connections. Earthing falls under class 1 insulation and it has this symbol. Now consider an electrical system shown here. Okay, so this is shown as a DC. You don't need to bother about that. Consider maybe it's an AC system. So you can see here one end is earthed. This is usually the neutral of the AC system, and the other end becomes the phase wire of the AC system. Now you have a bird sitting here on a single wire. So it rests on 2 feet and both feet are touching the same wire, which means both the feet are at the same potential. Therefore, no voltage is applied across its body to establish a current through it. Hence, the bird is not shocked. Okay. Here you see a man approaching and trying to touch, for example, the same wire. So he's going to touch this wire. So now you see, as soon as this person touches the wire here, he gets a shock. Okay, so this is because unlike the bird here, this person is standing on the ground. So you see the ground connection, and therefore he's actually making contact between 2 points. That is, the live wire is one point at a higher potential and the ground is another point at a lower potential, normally 0 volts, the ground potential. So therefore, due to this intentional earthing here, there is a flow path established for the current through flow through this person, and therefore he gets a shock. And you understand that this is due to this intentional earthing. So now you see here there is a path for the flow of current through the dirt into the ground, and so therefore there is a closed path established back here, and this we saw is because of intentional earthing. So a question arises here. If the presence of a ground or the earth point in the circuit provides an easy point of contact for someone to get shocked, why should you have it in the circuit at all? Which means, wouldn't an earthless circuit be much safer? So to understand this question, let's consider another scenario here. So consider the same circuit. So you can see here there is no earthing available at this point. The bird is not shocked, and so is the person. So this is because there is no closed path available for the current to return back to the supply. So there is no closed path available here. So when there is no earthing, despite the fact that the person's feet are still connecting and contacting the ground, any single point in the circuit should be safe to touch. So if the person is, for example, touching this end of the circuit again, he is not going to get shocked. Now consider the same scenario with the trees. Okay, so let's assume that a tree makes an accidental contact with the network, so which means the tree is providing an accidental ground contact. So for example, this happens when a tree branch touches the power line and it provides connection to the ground as shown here. Now in this case, if a person touches the same contact now, he gets shocked. This is because the accidental ground path is formed here through the tree. It completes the circuit for the shock current that will flow through the victim. Now let's go to the opposite of the previous scenario. So if the tree were to brush up against the top wire in the circuit, it would make the top wire safe to touch and the bottom wire to be dangerous. However, tree branches are only one potential source of earth faults in a power system. Let's now consider a different scenario without the trees. Now consider an ungrounded power system. So there is no ground here. So there are no trees in contact, but this time two people are touching the single wire. So one person is touching this wire, another person is touching the other wire. So with each person standing on the ground, contacting different points in the circuit, a path for the shock current is made through one person. So if the person is touching here, there is a path available through this person, through the ground, and through the other person. Through the other person here is also having the ground. So there is a path available, closed path available for the current through flow here. And even though each person thinks they are safe in only touching a single point in the circuit, their combined actions create a deadly scenario as shown here. This is exactly why ungrounded power systems are dangerous. So the only character guaranteed to be safe in this scenario is the bird, which has no connection to the earth ground at all. Now let's go back to the ground connection again. So in this figure, the person will not get shocked when touching the bottom wire, but if he touches the top wire, he will get shocked. So even if a tree touches, for example, the top wire here, the person touching the bottom wire will never ever get shocked. Thus, the presence of intentional earthing point in an electric circuit is intended to ensure that at least one side of it is safe to come in contact with. So this neutral point is always safe to come in contact with. Therefore, the conclusion here is by firmly connecting a designated point in the circuit to earth ground, at least safety can be ensured at that one point because there is no current in this path. Why? Because this point and this point are at the same zero potential. So current can never flow through the same potential points. The second question now is your shoe not protecting you? Okay, so normal footwear is not enough to guarantee protection against electric shock from a power system because the shoe may not be of proper insulating material, the soles may be too thin, moisture, dirt may reduce the insulating property, presence of conductive salts from the body sweat also provides a path for conduction. Overall, the shoes must be absolutely clean and dry in order to be effective. So special shoes made of rubber is good enough, but this has to be absolutely clean and dry to provide proper safety. Now you come back to another question 3. So if you get shocked by current through the earth, why not use the earth as a conductor in our power system? So we have an answer to that, which is called sewer system. Sewer is a single wire transmission line which is called single wire earth return. So single wire earth return. So this is a single wire transmission line for supplying single phase electrical power from an electrical grid to remote areas at low cost. The sewer line is a single conductor that may stretch for tens or even hundreds of kilometers. So 10 to hundreds of kilometers with a number of distribution transformer along its length. There is over 190,000 kilometers of sewer currently in use in rural areas of Australia. Compared to conventional lines, sewer is equally safe, more reliable, less costly, but with slightly lower efficiency and restricted load capacity. Separate earthing for function and safety are used in this system. Okay, so this figure shows a typical sewer system. So you can see here the power is supplied by means of an isolating transformer The transformer has a capacity of usually up to 300 kVA. This transformer isolates the grid from earth and changes the grid voltage, typically 22 kV line to line or sometimes 19 kV line to line, to the sewer voltage, which is 19. From 22 it changes to 19 or sometimes 12.7 kV line to earth connection. So it's from line to line 22 kV, it changes to line to earth 19 here, and a large sewer line may feed up to 80 distribution transformers. So you can see here the earth return path is utilized. So separate grounds for high and low voltage sites are used. So these groundings are here are functional earthing, not for safety. These are functional. Safety earthing is separate. So there is only one line going there, but then the earth is taken as a return path. Now consider the Australian pins. So this is a socket outlet. You have to mark here, note here the active, neutral and the earth connection. And similarly here you have the 3-pin plug which has active, neutral and earth. And this is the 3-dimensional view of the plug, 3-pin plug of Australia. Now it doesn't matter which way the pins are from an operational point of view, but it does matter for safety. Let's take a close look on what happens if we swap the active and the neutral wires in a pin. So every electrical conductor is protected by a circuit breaker. The purpose of circuit breaker is to prevent the building wiring from overheating as a result of excessive user loads being plugged in. So the active wire normally goes through a switch at the circuit breaker and the neutral wire goes to the equipment directly. So if you take the diagram, you have, let's say, the phase wire goes through the switch and the neutral wire goes directly to the equipment. So if you see, this is a load. So let's say this is the load and this is the external casing of the load. And this external casing of the load, it's earthed here and the neutral is also earthed. Now here you have the circuit breaker, which is a switch. Okay, so the neutral wire is grounded at the terminal box. So this is the grounding of the neutral wire at the terminal box in the house. So consider a scenario where the active wires gets accidentally connected to an ECP on a piece of equipment. So let's say here this active wire gets connected to the PCP accidentally. Now this creates a shock hazard. However, since the ECPs are connected to the ground through the third pin, so you can see here the ECPs are connected through the ground through the third pin, the active wire becomes connected to the grounding wire. So basically we are connecting the active wire through the grounding wire. Now the neutral wire is also connected to the grounding wire at the circuit breaker panel, which is here. Therefore, the grounding wire essentially becomes connected as a load. So the low resistance of the grounding wire causes it to draw a very large amount of current when it becomes inadvertently connected as a load, which in turn causes the circuit breaker feeding the active wire to trip. So you see here the current now, let's say the circuit breaker is closed. So when the phase wire gets accidentally connected to the ECP, the current flows through this ECP here, and then because it's also grounded, the current flows to the neutral wire this way. So the path is closed. So the grounding wire now essentially becomes the load in this circuit. So therefore, since the resistance of the grounding wire is very low, excessive currents flow through the circuit breaker, and the circuit breaker now trips because of very high current flowing through that. And therefore, the 3-wire system operates in a manner which transforms a safety hazard into an overcurrent condition, causing the safety hazard to be automatically cleared by the circuit breaker. Circuit breaker is used, therefore, as both an overcurrent protector and a shock hazard protector. So if we swap the neutral and the phase, what happens? Let's take that scenario. So let's take here, we have the neutral point which is actually earthed. Let's take, we swap the neutral and the earth, therefore the neutral gets connected through the switch then. So we have the same circuit here, and then let's say this is the phase. We are swapping the phase and neutral for the load. So this has an ECP again, and the ECP is grounded. Now in this condition, if the phase wire gets accidentally connected to the neutral, let's say the phase wire gets accidentally connected to the ECP, then what happens here? How does the path or the current flow? The current flow is through the ECP, of course through the ground, and since this ground is connected, it comes directly to the ground. So the current flowing through the circuit breaker is 0 now. There is no current flowing through the circuit breaker, and therefore even if this switch is closed here, since there is no current flowing through the circuit breaker will never trip. So therefore swapping the phase and the neutral, the active wire and the neutral wire, is a safety issue. Although under normal conditions, the operation of the equipment is perfectly fine even though the neutral and the active wire are swapped. Now the Australian pins are awesome for this pure fact because of the slanting nature of the active and the neutral pins, they only fit one way. And the normal colors for active wires are red and brown. So red and brown, active wires red, and for neutral wires it's usually black and blue for neutral wires, and for earth wires it's green and sometimes mix of yellow and green. So apart from earthing, we also have something which is called the bonding. So bonding is a process of establishing a required degree of electrical continuity between various conducting surfaces. So in contrast, the earthing is an establishment of electrical conductive path between a circuit and some reference structure. So earthing is actually a conducting path or choosing a reference. The main purpose of bonding is to equalize the potential rather to carry the fault currents, whereas the main purpose of earthing is to carry the fault currents. So the bonding conductor should be very short and direct wherever possible. So what we have here is we have something called an ECP. What is ECP? It's external conducting part, or you can define this as the external part of an electrical equipment which is made of a metal, therefore it's capable of conducting electricity, but usually it is earthed or it's functionally not connected to the equipment as such. And then we have PE, which is actually the protective conductor. So the protecting conductor is the earth wire which takes the ECP to the grounding point. And then we also have EXCP, which is extraneous conducting part. So extraneous conducting parts are any conducting metals. Extraneous conducting part is any part of the metal which is not an electrical device but any conducting part such as the water pipes in the house. Okay, so the ECP can be touched, and which is usually not live, but it may become live when basic insulation fails. So it is also referred to as non-current carrying metal part. Some examples of exposed metal parts are class 1 insulated appliances, armoring, lead sheath in underground cables, etc. So the extraneous conducting part is also a conducting part, is not forming part of an electrical system. So examples are metalwork of gas, water and heating systems, metallic frame of buildings. So the protective earth conductor is a conductor provided for the purpose of safety against the electric shock. Its function is to safely drain the fault current to the ground. This is also referred to as equipment grounding conductor. Now the bonding ensures that all the conducting metals, all metal parts in the house, for example the EXCPs, ECPs, everything are maintained at the same potential or the purpose of bonding is therefore to equalize the potential between the various metallic parts. So you see here that the gas piping is bonded to the electrical grounding system, which typically means bonding to the supply piping. So you have the ground wire running through and the gas piping bonded to the supply piping. So this figure shows the close-up of the terminal box in the house. So you have the neutral wire, the blue wire, the red wire is the phase wire, both coming into the house from the external line. So this is the service box, electrical service box. So you can see that the neutral service conductor extends back to the street where it is grounded at the utility pole or the transformer box. So the neutral terminal wire goes in there, and then the neutral goes directly to this, and the phase usually goes through the switch. And you can see all the ECPs are grounded through the grounding wire, and all the neutral wires are connected to the neutral bus bar. And similarly, there is also an earthing terminal bar in the terminal box, and the grounding wire, you see, it goes to the supply plumbing.